All right, part two of simple harmonic motion. And in this video, I'm talking about period and frequency in two different types of oscillating systems, a spring block oscillator and a pendulum. Um, so let's take a look at period first. Period, we use the letter T for that as its variable. It's a time, it's the amount of time it takes for a round trip to happen. So if that's a pendulum, it's the pendulum going one way and then back to its original spot. Or if it's a spring block oscillator, it could be the mass moving down and then back up to its original position. So it's going to be a round trip, the time that takes. And so most of the time we'll be working in seconds, but it could be any unit of time. So let's take a look. Let's say we've got a mass on a spring, like what we have right here. And we let go of that mass, and then it's going to stretch down to this middle spot, and then it'll stretch a little bit further, and then once it gets stretched down to here, it's going to be pulled back up, and so it'll go back through that equilibrium position and then back up to the top. And so this would be an example of a spring block oscillator. And if you were to graph those positions over time, you're going to get a sine wave. And so we've got a sine wave here that we can see. Let's take a look at that kind of over time there. All right, and so one period would be starting from here, going down, and then moving back up, the time that takes. The second thing we need to know about is frequency. And so we use an F for that, and that's going to be really the reciprocal of period. Instead of the time it takes for one cycle, it's going to be the number of cycles per one unit of time, seconds, for example. And so here we've got periods per unit of time. And so units that we can use for that, cycles per second, which we call a hertz, or inverse seconds. And so you may have heard of hertz before and talking about like computer processor speeds, talking about the number of cycles the computer can do per second, or with sound, so like different frequencies, different pitches of sound, the number of vibrations per second. And so a hertz, all that means is an inverse second or a 1/2 second. Basically, we leave out the cycles and just say the units are 1/seconds. All right, and so like I said, those are reciprocals of each other, which means that if you know the period or you know the frequency, you can do the other one by just taking 1 over that variable. All right, so for a spring block oscillator, which is the first example we're looking at, we've got an equation for the period of that. And that's this: T equals 2 pi times the square root of mass over K, which is the spring constant. Mass, we know what mass is. K, the spring constant, just the stiffness of the spring. And so if you want to calculate this period, all you need to know is the mass and the spring constant. If you can calculate those, you'll know what the period of that vibrating mass on the spring would be. One thing I want to point out is something that's not included in this, and that's amplitude. Amplitude here is going to be, when you take that spring and you stretch it out and then you let it vibrate, the amplitude is going to be how far it's stretching up and down. And that actually doesn't affect the period. So take a look at this. Here would be the amplitude. I'm going to start from that kind of middle position or equilibrium position up to what its maximum height is, or just on the other side of that, from the equilibrium position down to what its lowest point is. So that would be an amplitude. And the amplitude doesn't affect the period. You can stretch this farther or stretch it just a little bit. So it's oscillating like this or oscillating very far up and down. It's not going to affect the period. Anytime you have to do reasoning with this kind of thing, how does this variable affect this? A lot of times it's best to not go with your intuition if you know an equation, just based on the equation. Amplitude's not in there. All right. One other thing I want to point out with the vertical spring block oscillator is, what if you want to know, okay, how far did this stretch at this equilibrium position? So if it's just hanging from rest compared to if you just had a spring with no mass on it, how far has it stretched? And so here's one way we can do that, and we can draw a free body diagram for that. We've got the mass pulling it down, and we've got the spring holding it up, and so we have mg down and kx upward. Those are going to be equal to each other at this equilibrium position. These other positions, those are not equal, but at this equilibrium position they are. And so we can solve for that x by setting those two equal to each other. And like I said, those forces are just balanced at that equilibrium position. So let's set those two forces equal. We'll solve for x. We get that mg over k. And again, what I'm talking about here is what if we wanted to know from, this spring has no mass on it, and if we add the mass to it, it would just go down to this position right here if we let it just come to rest. And what is that distance d? Well, that's going to be what we just solved for right there. So that's one way that we could solve for how much does the spring stretch in that equilibrium position. If you wanted to know what that max height is, then you could say like, or the minimum stretch, you could take d, subtract a, the amplitude from it, and that'll give you this distance. That's the minimum stretch during its oscillation. Or the maximum stretch would be d plus a, and you get that maximum stretch during its oscillations. All right, let's look at pendulums now. So let's draw a pendulum here. I've got a pendulum here. We're going to pull this back some angle theta right there, and we're going to let it go, and it's going to swing down and to the left, and then back up to its original height, and that would be 1 period of the pendulum. And we got an equation for that too. T equals, or period equals, 2 pi times square root of length over gravitational field strength. The length here is the length of the string from that point of rotation there down to the pendulum bob, or the mass at the end of the pendulum. G is 9.8 meters per second squared here on Earth. So if you took this pendulum to the moon, it's going to have a different period. Now, one thing that's really interesting here is, look what's not in here, mass. So it doesn't matter what mass you have on your pendulum, you're going to have the same period. What does matter is the string length and the gravitational field strength, so like what planet you're on. And anytime you're using anytime you're reasoning through the effect of one variable on another here, keep in mind there's a square root. So for length, for example, if you wanted to double the period of the pendulum, you wanted to take twice as long to swing back and forth, you'd actually have to make a pendulum that's 4 times as long, because you take 4 times L, square root of 4 is 2, so that would make a period of twice as long. So keep that in mind whenever you're doing any reasoning with this. Okay, so let's take a look at this now. There is a force that's causing this to be restored back to its kind of equilibrium position here. So let's take a look at what that force would be. So I just do a free body diagram for the pendulum bob, or the mass here, and there's gravity pulling it down, and then there's the string, which is a tension force pulling it up and to the left. Now, clearly these forces are unbalanced, but there's actually a couple components that do balance out, and we can solve for this net force pretty easily. Let's go ahead and resolve that mg, that gravitational force, into a component that's parallel with the string and one that is perpendicular to that string. And so we've got the two components here of this downward force, a parallel and a perpendicular component. And it turns out here that the tension force and that parallel component of the weight are equal to each other. So those two cancel out. All we're left with is this perpendicular component. We can do a little trig to find out what that is. Let's put in our angles there. Theta, same angle theta right there. And we can do mg sine theta to find that component there. So that's the only part of this force that's unbalanced. That's going to be our net force, or what we call the restoring force here. That equals mg sine theta. Now, what if you want to know, well, how do all these things affect the acceleration? Well, we can just use Newton's second law. A equals F net over m. We'll substitute in mg sine theta for F net. You'll see there's m and m, so the m's will cancel out, and we'll get acceleration equals g sine theta. So let's say that the test asks you, okay, what's the, you change out the mass, how does that affect the acceleration? Well, you could just solve for this, look and see, well, there's no mass in this equation, therefore the acceleration is not affected. The only things that affect the acceleration are g, the gravitational field strength, and the angle. So how far did you pull that back? That would affect the acceleration. Or if you want to know about the restoring force, in that case, or the net force, in that case, the mass does matter. So that's how you can use these equations to answer questions like that. All right, next thing, and this is common in pendulums, is to do an energy analysis. So look for this whenever you see a pendulum problem that's asking about velocities and heights and all this sort of stuff. Well, let's do a conservation of energy analysis. All right, so first thing is, let's just mark these two heights we're going to measure from the middle of the pendulum bob. And let's call this position A and position B just for simplicity. Now, at this point A, we'll call this, say this is the highest point. That point A, the velocity is zero. It was moving up, it's about to move down, so it's a zero velocity at that point. Hopefully you see where I'm going with that in terms of energy. And the height is maximum. That's the highest that that's going to go during this back and forth motion. At point B, we're going to have the opposite. That's where the velocity is maximum. It's that lowest kind of part of its trajectory there. And the height would be zero. And we're going to define this lowest height as zero, again, for simplicity's sake. And then this max height would be h, that difference in height right there. And so we could solve for, let's say we're solving for the maximum velocity. We want to know what's the max velocity at position B whenever we raise our pendulum up to a certain height, h. So let's set up a conservation of energy analysis here. At the beginning, at point A, we just have gravitational, no kinetic energy. And then at point B, we just have kinetic energy, no gravitational, because we're now at our height of zero. And we can substitute in our equations there, mgh equals 1/2 mv squared. Mass is going to divide out on both sides, and we get gh equals v squared over 2. And then we could solve for v, and we would get square root of 2gh. So if you want to know what's the speed of our pendulum down through this bottom position there, you can just take square root of 2 times 9.8 times whatever that height was. Notice the mass didn't affect that velocity either. Keep in mind though, in SpringBlock oscillators, either vertical or horizontal, usually the mass does affect the period and these different things. All right, that was simple harmonic motion. Thanks.